Hello everyone, welcome to Algo-holic, the place where you learn not just the solutions but the thought process behind solving problems. Today we're solving the problem jump game. We're given an integer array nums. We're initially positioned at the array's first index, and each element in the array represents the maximum length of a jump. We're supposed to return true if we can reach the last index by jumping. Let's look at an example. We start off at 2 and we're supposed to find out if we can reach the last index, which is 4. So from 2 we can either jump here or jump here. And from 3, we can directly jump to the last index. So therefore, the output of this example is going to be true. By the way, there can be multiple solutions. As you can see, from 1, we can make a jump here, and from there, we can jump to the last index. Let's look at another example. We are starting at 3, and we're supposed to find out if we can reach the last index. So from 3, the maximum jump is going to be 0. From 0, we obviously cannot move any further. From 2, again, the maximum is going to be 0, so we can't move any further. From 1, the maximum is going to be 0. So there is no way for us to reach 4. Therefore, the output is false. So what is the brute force solution to this? Let's take the same example. Let's start off with the first value, which is 2, which is index 0. We have two choices. So we can either jump to 3 or jump to 1. Index of this is going to be 1, index of this is going to be 2. Then we have three choices from here. So jump to the first one, jump to the second one, or jump to 4, which is the answer. But let's keep going to understand the time complexity better. So this is going to be 2, this is going to be 3, and this is going to be 4. From here, we have one choice, which is the next one, which is position 3, then 4, which is also another answer. From here, we can jump to the next one, which is index 3, then 4, which is another answer. From here, we jump to 4, which is the answer. So there are many ways to get to the answer. And what is the time and space complexity of this? Well, the depth of the tree is n. So the space complexity is going to be big O of n. And what is the time complexity? Well, the number of childs each node can have is the value of the node itself. As you can see here, this has 2 children, this has 3 children. So in a way, for every value, we can either include it or not include it, because from 3, we can either make the jump to 1 or skip it altogether. So we can either include 1 or not include 1. So that is the main idea. And since we can either include a number and not include a number, that is 2 ways. And getting to that number is going to be n ways. So the time complexity is going to be 2 to the power of n, and space is going to be big O of n. This is obviously not a very good solution. So what is the best solution? The way I'd like to think of this problem is kind of like solving a maze. So you have start, end, maybe a few blocks in the middle. One here, one here, one here, maybe one here. So how do you arrive at the correct solution? Maybe you try this one, you fail, try this one, you fail, go here, try this one, fail, fail, and then maybe arrive at the correct solution. Or you might get lucky and arrive at the correct solution in the first try. That happens too. Now, the way I solved this problem is starting off at the end instead of starting off at the start, because I knew that whoever designed these kind of games, they kept more branches at the beginning than at the end. Essentially, by starting off from the end, you're exploring fewer branches. So how about we use the same logic to solve this problem? Instead of starting off from the start, how about we start off from the end? Taking the same example to a slightly modified example, 3, 0, 1, 1, and 4. Instead of starting off from 2, how about we start off from here? Now, can we reach 4 from 1? Yes, we can, like this. So let's move the goalpost. Instead of trying to reach 4, how about we try to reach 1? Because we know that 4 can be reached from 1. So if we reach 1, we also know that we can reach 4. Move to the previous index. Can we reach the second one from the first one? Yes, we can, like this. So let's move the goalpost. We are trying to aim this one now. Previous index, can we reach 1 from 0? We cannot, so we are not moving the goalpost. The previous value is 3. Can we reach 1 from 3? Yes, we can, like this. So this becomes our goalpost. Finally, 2. Can we reach 3 from 2? Yes, we can, like this. Therefore, we can conclude that we can also reach 4 from 2. Now, what is the time complexity of this? We're just making one pass. So time is going to be big O of n, and space is going to be big O of 1 because we're not using any extra space. this is the most optimal solution. Let's quickly go to the brute force solution. We define a helper function, can reach end. Two parameters, we take position and the array itself. Here, the base case is going to be true where pos equals length of nums minus 1. So we've reached the end. If we did, we return true. Let's calculate the jump now. So the jump is going to be nums of position and from where you're making that jump. So that's going to be position. Let's put this in a variable max jump. Now this can overflow. So let's put it inside a minimum function where we take length of the final element. Sorry, length of the array. So this is not going to overflow. And if this were to be the larger one, what happens is this is just going to be returned. And in the next iteration of the function, it's going to execute this case. Now we also need to note that max jump is not the only scenario we need to consider. We need to consider every scenario from 1 up until max jump. For example, if max jump is 4, we need to consider a scenario of 3, 2, and 1. We need to make all those jumps. So for that, for let's say next pos in range. So jump has to be at least +1. So up until the max jump. Now here inside the if condition, we execute this. We call this function recursively. So next pos and nums. If this is true, we return true, else we return false. In the end, we just have to call this function. So can reach end. 0 because that's where we'll be starting from, and nums. So I'm not going to submit this because it's likely going to fail because of how long it takes, but I'll just run the base test cases. Yup, it works. Now let's code up the optimal solution. We define the goal, which is length of nums minus 1. Now we run a loop from the second last position. So for I in range, length of nums minus 2. We don't do it from the last value because we can obviously reach the last value from the last value. So it doesn't really make sense. So minus 1, minus 1. This is just Python's way of running a loop from the second last value up until 0th index. Don't have to worry too much about the syntax. So if now let's try to visually understand what we're doing. Currently, we are here. We need to check if we can reach the goal. How do you do that? We take the I value. So this is going to be this. And now we need to take the value of this, which is going to be the jump. So I plus nums of I. So combined, this has to be more than or equal to the goal. If it is so, we move the goalpost. So goal equals I. In the end, all we have to do is execute the same condition from 0. Sorry, I missed. Yeah, you don't need that because this is going to be 0 anyways. So this should be the final answer. Yep, and it is the most efficient solution. Let's look at the solution in C++. We define the goal. The loop looks much better in C++. It's much more informative. And here we move the goalpost, and in the end we just check if goal equals 0. We can also run this condition over here and make a few modifications, but this is much more cleaner. Java code looks pretty much the same, where the loop looks exactly the same as C++. Here's the condition to move the goalpost, and in the end, we check if goal is equals to 0. So that's all for today. I hope you found this video helpful. Your feedback helps me make better content, so please share your thoughts in the comments below. I'll see you in the next one.